So today I'm going to talk about reinforcement learning for robot control. I'm mainly going to provide the high-level picture. I'm also going to talk about some of the things my group has been working on, but really the focus is more on getting you an intuition on what the specific challenges are. So reinforcement learning, I suppose everybody's familiar with that who has at least played with robotics in some sense or other, just to get an idea. Oh, okay. So maybe half of you. Good. So robot learning. Why do we want to have robot learning in the first place? This is how you would very traditionally program an industrial robot. So you have this lin and then two thingies. That's a linear movement from point to point, and then you can program that. Works very nicely as long as you stay in a setting like you have here, where you have a fence nicely separating the robots from humans, and the robots do the exact same thing 24/7. So that's not very neat robot learning or reinforcement learning. Where it gets more interesting are all these other interesting settings. Autonomous driving, in a greenhouse environment, in a home environment, or in care. So what's the problem there? You have uncertainties and variations in objects. Think about the robot in the greenhouse where every tomato is slightly different. The environment, natural environment, light is going to change. The growth of the plants is going to change. You don't want to buy a separate robot for loading your dishwasher and unloading it. So it should also be able to do many different tasks. And if it's supposed to interact with humans, you get a lot of uncertainty and variations there. So that's occurring in all interesting robot domains. So if you look at reinforcement learning in robotics, on the right, you can see a few snapshots. The oldest one on the top is from 1992. That's the oldest one we could find. Has been applied to all different morphologies of robots. The obvious big challenge is that it needs to be safe with real robots. You don't want to damage the robot itself while it's exploring, and you also don't want to damage the environment or even worse, people that might be around. Related to that, you want to be able to learn fast. If you do random exploration, you get lots of wear and tear on the robot. So you typically have to deal with very small amounts of data, unless you Google and similar companies, and when you can afford to have this really army of robots working day and night for a couple of months just to learn how to pick up a simple object out of these bins there. So in general, while in principle reinforcement learning or deep reinforcement learning would work, and if you can do it, it's very impressive, but it's everything except practical. To get around that, you need to incorporate some form of prior knowledge, or conversely, have as few open parameters as possible. And then the last thing you need to keep in mind is, it depends a bit on what you do. If you do more low-level control, at least, then real-time computations become very important. If you're thinking about more high-level tasks where you just think about, okay, I need to move over there, and then you have a lower-level controller taking care of that, then it's not as critical any longer. There are many different ways of classifying reinforcement learning algorithms. This is one of the typical ones. I'll just very quickly run through those and give an example of one of those pillars each and an application in robot reinforcement learning. So starting with optimal control, the one I'm going to show you is, I guess some 20 years old now, is on acrobatic flight. That's a remote controlled model helicopter where they did what they call apprenticeship learning, with the idea that they extract the optimization criterion and kind of the maneuvers from demonstrations of a professional human pilot, but then the actual reinforcement learning and control is based on is model-based effectively. So using a form of optimal control there. Then we have value function methods, where at least if you are in a more classical setting, the big challenge is on how to deal with continuous states and actions, which you inherently have in robotics. So you can discretize either the states and or the actions. more often than not, you'll instead see function approximation for, again, either the value function or maybe additionally also the policy. Here is an older example from, I think, around 2006, 2007 on learning to dribble this ball in a robo-soccer environment. Where they have some preprocessed data. They also collect some interactions by randomly interacting with the real system. And they also, at some point also have somebody come in and mess around with it to kind of mimic the opponents. And then they very successfully applied that here. That's kind of the final policy where it's very closely keeping the ball to its kicker. And they very successfully used it and also in a competition against another team. So final pillar, policy search. So effectively actor-only methods. This is one of my very old videos on using policy search to learn ball in the cup. So the goal is to catch the ball in the cup. That's yet another way of getting prior knowledge in there, starting with a demonstration. So you have kind of warm start learning process. And then after some 15 trials or so, it kind of works, but it's still off by a few centimeters. After some 45 trials or so, it starts to go in once in a while, but more often than not, it does something like that or just bounces off. So here you're going to see the bouncing behavior, and then after 100 trials or so, it has nicely converged. So the examples I've shown you so far, they were all very classical, using quite a lot of hand engineering for the states and the action. But that then changes if you come into the area of deep reinforcement learning. So deep learning goes from, you could say, from raw sensors to a form of knowledge or a good representation of the state. Classical reinforcement learning is more going from states that are already pre-processed from the observations and going to actions, and then deep reinforcement learning obviously is the whole thing. Also here, an older one, I think that at least for me was the first paper that really showed that deep reinforcement learning now is a thing in robotics. Here they managed to learn in the real world, but they used, again, a form of prior knowledge, in this case, instrumented training. So that means that they had more information while doing the learning, so privileged information about the positions of the objects and so forth, which they don't need any longer when then deploying it. So how it works is actually a very complex system. So what they do is they collect samples from the real world. They use that to learn a model of the system. Then they use a form of optimal control to optimize local controllers. And then that gets deployed again. They train a neural network to mimic what that optimal controller does. And on the perception side here, they pre-train it on some images and then also use that here in the network to do the end-to-end learning. So very complex system, but it actually worked amazingly well. What you often see in robotics videos is the X4 or X10, how much it's sped up. This is in real time, which is extremely impressive. Can nicely generalize, and I tried it on a number of different tasks. And also, let me try to scroll forward a bit. Also with a bunch of distractor objects and these kind of things. So that was a somewhat older example. In the meantime, the field has developed quite a bit. When I was starting in around 2008 or so, we had a single session in a ginormous robotics conference with, I don't know, 14 tracks in parallel on robot learning, not robot reinforcement learning, but robot learning. Now it's the most popular keyword, and there's a separate conference and a huge field doing robot learning. The reinforcement learning, I think very much a big part of the community moved to sim to real. So the idea of learning in simulation and then transferring it to the real world. So what are the advantages? You can run the simulation potentially faster than real time, so train faster than real time. The simulations are inherently safe. If your legged robot falls over, okay, just reset the simulation, no harm done. You can reset them to any arbitrary state, so you can reset them to something that is interesting, where you can actually learn a lot. And you can evaluate different settings. And you can also have multiple simulations run in parallel and then collect even more data. So what you can often, so there are two different flavors of that. You can pre-train a simulation and then fine tune. So you only need very little data from the real world, or you attempt to do direct transfer. And also for that, there are two different flavors. So you can either make the simulation as realistic as possible and then hope that it's realistic enough so that what you learn in the simulation also works in the real world. Or you can try to make the behavior robust. So that's this idea of domain randomization. This is an example more on the perceptual side, where you train it with a whole lot of variations that are typically, the set is typically broader than what you expect to encounter in the real world, so that the behavior is then so robust that it directly also works on the real world example that's here on the very right, which is then supposed to be kind of within this distribution that it saw in training. That makes it robust, but obviously that in most cases also comes at the cost of some performance loss. Here's a very famous example of that. I guess many of you have seen that. OpenAI learning to solve a Rubik's Cube purely in simulation and then applying it on a real high-dimensional robot arm. Again, here the randomization in the perceptual side, you can see there. Let me just play the video. And what's also important to know is that they actually did not learn how to solve the Rubik's Cube. The solving the sequence and in which order you need to turn what, that was done in a very classical planning style. What they learned is the physical control on how you turn the individual layers of the Rubik's Cube and these kind of things. So that's what you see quite frequently, that what you think is hard, at least for humans, often that's quite easy for robots and the other way around. And then they messed around with it. So here with a whole lot of distractors changing the dynamics and so forth. And it really is extremely robust. Yes, that's very fun. Okay. Few more recent things. You could actually get quite a few Nature and Science papers out of that if you do it properly and you have some impressive demos. That's not, well, that's kind of robotics, but not really. That's Sony learning to compete human champions of Gran Turismo, so a computer game. This is a bit more recent from 2003 from University of Zurich, both science and nature on beating world champions in drone racing. So the goal is to fly through these kind of gates as fast as possible, having only first-person view of the drone. And they actually managed to use a neural network and deep reinforcement learning to make it work on board of this drone with just the camera attached to the drone and not using any external cameras or motion capture systems. So that's very cool. Yes. So it's a complex system. It's using a whole lot of things, but kind of the core of it is the reinforcement learning in simulation and a whole lot of smart engineering to make the visual processing fast enough that you can do it. As far as I know, yes, the latest version. Yeah. So the big question is, okay, does it always work? And okay, these demos are extremely cool. So the question is, will it transfer? And if you just do it blindly, and you get these kind of things, you get really crazy policies. So if you do it naively, probably no. So a few high-level guidelines on how to make it work. Yes, you can go quite far by making it robust and doing domain randomization, both for the transition functions, dynamics, and the perceptual side. But still, it's very helpful to minimize the model mismatch. You always need to keep in mind that all models are wrong, and then specifically try to mitigate some relevant mismatches. There's also quite a few tools for that. Isaac Gym, which is called Isaac Lab nowadays. On the left, you see a massively parallel training of a quadruped robot, and they actually now are shipping walking behaviors trained with reinforcement learning in simulation on commercial products. And some other manipulation examples. There's also Unity is another one that maybe the physics aren't that great, but the perceptual things are a lot better. And there are many more. So to dive a bit more into the details there, what are common pitfalls? And I'm going to show you some of our own work now. And just to illustrate things, it's going to be an extremely simple system to start with. So that's an inverted pendulum. In this case, it's a weight on a disk, which is not the same thing effectively. On the left, we have a simplified simulation. We train in that. And then that's what's happened. So that's here the arrow effectively. In simulation, it does extremely well. In reality, as you can see in the bar and also in the animation, it just fails horribly. If you then do domain randomization, so to make it more robust, then the gap, the domain gap when transferring from simulation to reality here is a lot smaller, and it actually works. And in this case, yes, you can see also in simulation, it does a tiny little bit worse than there if you have just a single model and no randomization. What you quite often also do in robotics to make sure that you don't damage your own robot is that you introduce some additional safety features, some kind of lower level controllers. And there you also need to be careful. So this example, it's both in simulation, but it's the same holds if you transfer it to the real world, is in training. We simplified things a little bit and did not consider the collision avoidance component there that we have as an additional safety feature. However, that kind of very subtly changes the Markov decision process and maybe even changes the Markov property. And then it doesn't work any longer if you try to transfer it. So also there, usually it's a good idea to mimic what you're going to have on the real system as closely as possible in the simulation. One other thing that you have in physical systems, and if you put multiple components like cameras and actuators and maybe different sensors together, is delays. So even for something like that, for a very simple system, we just have the reading of an encoder. If you ignore the delays, again, transferring from the simulation that ignores the delays to the real world doesn't work. And again, if you include these kind of things in simulation, that works a lot better. Then the big question is, how do you actually model them? And how do you estimate them? And I'll come to that in a few minutes. And one other thing, especially if you use something like the robot operating system, ROS, which is a middleware for connecting different components in a robotic system, is often it's an asynchronous framework where you have little modules running at their own rate, and then they need to talk to each other. And if you don't take that into account in your simulation, that can potentially make transferring it to the real robot a lot harder. So, like I was already saying, there's quite a few frameworks out there for sim to real that allow you to do massive simulations in parallel to collect massive amounts of data. But quite a lot of them actually don't consider these challenges and potential pitfalls I was just mentioning explicitly. Two of our PhD students came up with a new framework that's called EagerX, Engine Agnostic Graph Environment for Robotics, which is a Python framework that enables you to define OpenAI gymnasium compatible environments that work both in simulation and the real world. And there the idea is it's also node-based, so you have the different modules. And then how it's set up is that you can really directly switch out the parts from simulation to the real components and have everything else exactly the same, which avoids a whole lot of these pitfalls I was just showing you. So here you can see you just saw a direct transfer from simulation to the real robot by just swapping out one of the modules. And then here we used it to train a reinforcement learning agent of the drone to land on this inclined platform with a moving system. And you can also use it for things beyond reinforcement learning. So this is having a large language model in there so that you, and in this case, actually imitation learning to put these bolts into the corresponding holes or tubes, which is inspired by an engine assembly task. We also, associated to that framework, we also have things that allow you to estimate the delays and how the different systems, subsystems interact. So this is a follow-up paper called REX. What you see on the left is a top view of a quadruped that is lit up trying to fly in a circle. On the left, that's using our framework first to estimate the delays between the various components and then doing reinforcement learning on top of that. And on the right, that's just a naive simulation, not explicitly estimating the delays. And you can see that on the right, it's wandering around quite randomly after some initial things, and that's just accumulating errors and then not working as well. So sim to real, if you can make it work, it's awesome, but you have to be smart about it and really also know your system and know where the potential discrepancies between the simulation and the real system are so that you can account for them while training. That much on sim to real in robotics. And I wanted to spend the last 10 minutes or so talking about a few other ideas on how you can use reinforcement learning in robot control. First one is a paper we're going to present at a conference in a couple of months, where we, like many other people, were looking into what can we actually do with the foundation models, large language models. The idea we came up with here is to use them for a few different things. We use them for perception. That is just very standard, and we just use it out of the box. The interesting bit here is that we actually use a large language model to guide the exploration of the robot. So effectively, the idea is that the LLM encapsulates some common sense knowledge, at least a crude understanding, that we can use to help the reinforcement learning agent to discover highly rewarding policies more quickly. So that looks something like this. Like I was just saying here, we have a visual language model that we use to do the perception and detect the locations of the various objects. We have a user instruction in text form, which matches it also to that. So that effectively is just used to extract the observation space, which then serves as an input for the reinforcement learning part. And then here, that's the new, come on, why doesn't that work? No, in yellow here, we switch between doing very standard reinforcement learning style exploration using epsilon greedy or on-site Uhlenbeck in this case, I think, versus using LLM exploration where it actually generates code that is then used for exploration. And then in the end, it's a residual action formulation. So kind of what we learn is an offset on top of what the LLM already wants to do. So then the obvious question is, does it really help? The obvious answer is going to be yes. However, it's a bit more nuanced than that. So this is a very messy plot. Can you see my mouse now? No, let me try once more. Here. So what we have here are different levels of which percentage of the time the LLM exploration is active, ranging from 0% to 90%. Using just standard exploration, that's the baseline here with the dashed line. And you can see that if we don't do any LLM exploration, it's very slow in blue here. With 10%, it's still extremely slow and almost doesn't work. 20, 30, 50% works extremely well. And then if you purely rely on the LLM to 70, 90%, then we are again in the region where it doesn't work that well. So really, the sweet spot is in having both the LLM. If you go to 100%, then you would just use the LLM, which wasn't trained for that task and has just some crude knowledge on how things are supposed to work. So that obviously will slow down the learning process a whole lot. One sec. And if you don't use it at all, then you fall back to the standard reinforcement learning. Yes. Yes. I'm not so the LLM policy is effectively frozen. So that's always going to be doing the same thing. We're not refining the LLM. We're only learning a separate reinforcement learning policy. Is that what you mean? So it doesn't make it, oh, okay. Sorry, that might not have been entirely clear. So the LLM doesn't know anything about that. This is an exploration task. So it doesn't try to find the best possible exploration action. What it does is it sees a certain, let me just show you the video. It sees a certain configuration and a command prompt. And then based on that, it's going to generate a policy. So it's a code to policy kind of setting. And then whatever it would generate for that is used as kind of exploration action. And then here, that kind of comes back a little bit to the sim-to-real things I was talking about beforehand, is because we're using all those standard blocks for the visual perception and the language processing, and then using a more higher level action that already is robust enough to allow us to directly transfer from what we learned in simulation to the real robot. Now, moving to something quite different, central pattern generators. So that's neuroscience inspired, something you have in the brain, some kind of oscillators that are coupled, which generate periodic movements for locomotion in animals. That's been around since quite a while, also in robotics and also in the earlier days of robot reinforcement learning. And recently we were looking into that once more, and it's actually very interesting. And we compared it to very nowadays common deep reinforcement learning setups. But you see open loop in blue, that's using these central pattern generators. And then you see a whole slew of other deep reinforcement learning baselines with their more or less standard policy networks and value function networks associated to them. And then kind of where you want to be. Ugh, come on. No, it doesn't work. Is as high as possible. There you can see that at least for the left part of the plot, it does as well. And then when you get into the really high performance, very, very detailed control things on the right, only SAC really is the odd one out and performs a lot better. While it actually overfits to the simulation and the very specific environment. So why is that still interesting? Using these central pattern generators is a whole lot more efficient. So here you see the runtime in minutes for training the different reinforcement learning agents. And here it just takes 2 minutes, and you don't even need, we didn't even put it on a GPU because it's so fast. So that's like 40 times faster than some of the other things. And also, if you compare the number of parameters, so here you have a log scale versus the score it gets. Here is our open loop method that does very well with a tiny amount of parameters. And then again, only SAC is the odd one out that does a lot better, but also needs, 5 orders of magnitude more parameters. And like I was saying before, it's this then really overfitting to the simulation. And if you try to do any sim to real transfer, then the policy you learn with SAC simply fails horribly. So in that sense, the central pattern generators are a lot more robust. So here is an open loop movement in simulation that is learned. And then, one sec. That's the same policy ran on the real robot. Very nicely transferred, while the SAC one really was exploiting some nitty-gritty details of the dynamics and didn't move at all. And then to get the performance up even higher, so the central pattern generators, how we use them for the plots I showed you were open loop, but then if you add a little bit of a feedback controller type, also learned with reinforcement learning on top of that, you get the best of both worlds. The final topic I wanted to talk about briefly is yet another way of getting in prior knowledge, in this case from a human teacher. So that's a very standard reinforcement learning control whatever loop. What we now have additionally is a human teacher who is going to be in the center and observing both the states and actions the robot does, and then is supposed to provide some kind of feedback. Could be a replacement for the reward function where the human goes yes, no, which isn't that demanding for a human teacher, but like a sparse reward setting, not very informative for the robot agent. Or if you go the other end of the spectrum, you could go back to imitation learning, where the human teacher is supposed to provide the perfect action for the state the robot is in currently. And you can do many things in between. Preferences, in this case, we're actually going to go with corrections, which are kind of a relative direction. So it's like something like move more to the left, move more to the right, and not absolute values. So how does that look like? that's a kind of a loop of a policy search approach, where you also have a form of exploration, which are typically perturbations, random exploration. And here we modeled the human teacher feedback corrections in this case as a form of exploration. That in the end looks something like this. That's going to be the same example I had almost as the first one in my talk, using doing ball in a cup. In this case, we can actually start from scratch. So we don't need to provide any initial demonstrations. Everything is initialized to 0. What we now have additionally is a teacher providing these corrections. And then within 20 trials or so, we can actually learn to catch the ball in the cup. So now that's really at the speed of how quickly also an average person learns to do this task. To show you a little plot related to that, here we have the number of rollouts, so the number of times we tried to do this task. On the other axis, that's the cost, so lower is better. The first plot I'm showing you here is starting with an initial demonstration, so we had actually a human person practice quite a bit to provide a good successful demonstration, and then the reinforcement learning had to refine it. So that's if you use pure reinforcement learning, that's the red curve there. So from maybe 30, 40 trials onwards, it succeeds. In green is using only corrections and then an imitation learning setting, and in blue that's the combined approach. So what you can see that both of those are very quick in the beginning. Using only corrections and imitation, it levels off here just because you hit the limits of how precise a human can be and the reaction times and these kind of things. And with the blue one, the combined approach, you get the best of both worlds. So that's not very impressive yet. It really changes if you do what I was showing you in the video a few seconds ago. So starting from scratch, no initial demonstrations, then using pure reinforcement learning, actually tried and managed to do it on the robot. Takes some 200 or so trials before it succeeds. While if you have the human in the loop additionally, you're still somewhere around 20 trials or so. So that's one very promising way of getting human insights in there, relying on the fact that now instead of the LLM, the human teacher can steer the robot into a region where it will collect high rewards and succeed, and then the robot can play to its strength and use reinforcement learning to fine-tune it. So to sum up, there's some specific challenges in robot reinforcement learning. You have to deal with small data, at least if you are thinking about doing reinforcement learning on a real robot, and you need to carefully think about safety while learning and exploring. That's very obvious, but then also when deploying it and freezing the learn policy, even there, that's one of the important things you need to keep in mind. And during this talk, I talked about quite a few different things that allow you to gain tractability by including prior knowledge. Can be pre-structuring the policy in a smart way, can be starting with demonstrations and fine-tuning, doing sim to real, using foundation models, using human teachers, and I'm pretty sure there's many, many more. Thank you. Mm-hmm.
Basically, just want to find out that price. If everyone wants to spend a whole lot more time on like playing I don't know, you get both the simulation and the real world. In order to spend less time in simulation, what would be advice?
So my advice would be to spend quite a bit of time with the real system before you start doing the reinforcement learning. Otherwise, you get some form of iterative process where you spend a whole lot of time training your reinforcement learning agent and figuring out, doesn't work, this is whatever inaccurate. You need to change the simulation and rerun everything, and you do a couple of those iterations. The other important thing is to very carefully think about what level of fidelity you need and actually at which level you want to do control. So if you want to do low-level control at the level of motor torques, then obviously the simulation needs to be a lot more accurate compared to saying you do position offsets or something of the end effector, where you have a lower-level controller that is going to more or less absorb all the differences between what you have in the simulation and on the real robot. Mm-hmm. Excellent question. So the one way is fairly easy to explain. Joint states alone, if you want to interact with any objects in the environment, are not enough just because you don't know where the objects are. So there you need some additional sensors like a camera. The other way around, why visual camera images are not sufficient is a bit more tricky. In principle, they are, if you have, maybe some stuff is covered and the resolution isn't so great. But just generally speaking, you get the joint sensor information for free almost from the robot anyhow. It's a lot cleaner, it's a lot closer to the real state, and in practice it just makes learning a lot easier if you have this high quality data to include it additionally.